All right, we're recording. This is October 22nd, 2020. This is the review session for exam 3 in discrete math. So I'll post this. This will be in the Teams calendar for this meeting, but also I'll put it on the course webpage. Well, let's see. Let me disconnect my tablet from its base so that I can write. All right, there we go. So I'm going to turn off my camera. Let's see. Okay, can everybody still hear me?
Yeah, I can still hear you.
Yeah.
Yep, I'm just getting my I should have got this ready beforehand, my drawing pad. All right, then I'm going to share. I've got my drawing pad open. I'm going to share my screen, or share that. Let's see. Okay, can everybody see that?
Yep.
Okay. So here we go. Well, I guess to make sure that we get to the more recent stuff, let's start with the more recent stuff, the idea of relations. Nathan mentioned the properties stuff, the reflexivity, symmetry, and transitivity. You others, do you have any questions of any, or Nathan, do you have any specific questions about that stuff, or just sort of general questions? All right, well, why don't I jump in with some examples of some relations. So maybe I'll throw out some examples of relations and ask for feedback from you about their properties. So let's start with relations on the set of real numbers, because we can draw graphs for those. So let's call our relation R on the set of real numbers. And let's define it this way. So for that relation, who can help me out with its properties? Is it reflexive? Is it symmetric? Is it transitive? And how would we explain those things? Anybody have any idea about that?
So it should be reflexive because it's less than or equal to. So if I have x is less than or equal to x, that would work because x is equal to x.
Okay, good. So can you be a little bit clearer? So if you're trying to explain to somebody the justification and they don't quite get it, what can you try to explain a little bit more thoroughly why it is that you said what you said?
So in order for a relation to be reflexive, then it must be true that x r x is true. The relation is
Good.
true for x. So when I said, x is less than or equal to x, I'm just plugging in x for y because x r x has. So x is less than or equal to x would be true because x is equal to x.
Yeah, good. So in order to do this, you just say, well, xrx is, and that's always true. Now, can you think about how you'd illustrate this with some kind of picture? What would you draw?
Would you draw just like a line, like y is equal to x, and then shade in the area that's to the left of that line, maybe?
Exactly. Good. So in other words, you're making a graph of the relation. So here are the axes, and the graph of our relation is going to be this line that has y equals x, and then all the points above it are part of the relation. And so your illustration of what you just said about reflexivity would be, in terms of this picture, you could just say, well, every point on that main diagonal is part of the is part of the graph of the relation. And remember that the relation is a set. It's a subset of the xy plane. So the graph of the relation is just a picture of all the elements that are in the set. Okay, who can talk about symmetry? Is this relation symmetric?
So no, it's not symmetric because for symmetric xry and yrx have to both be true. X is less than or equal to y is true, but y is not necessarily less than or equal to x. So therefore, it's not symmetric.
Be careful what you said. You said that xry and yrx have to both be true. They don't have to both be true. Basically, if one of them is true, then the other one has to be true. So now, me see here. I don't have my keyboard. So somebody else remind me so how does this symmetry property go? What's the statement that a relation is symmetric? Well, here I'll go ahead and jump in on this one. So Nathan, you're saying that that's not true. Now, say your explanation again.
I said that x by the relation x by the definition of the relation x is less than or equal to y, but y is not necessarily less than or equal to x. Y can be greater than x, so therefore it's not symmetric.
Yeah. Hang on here. Let me make a note. Let me pop out for a second and see who else is joined. Oh, still just the three of us. Okay, well, Sienna and Eden, do you have any comment? So this is symmetric. What is the statement of not symmetric? This sort of goes back to the idea of negating a quantified statement. So to say that a relation is symmetric is this statement here, which is a quantified statement. So the statement that a relation is not symmetric, what's the statement of that?
I think that it would be that there are elements for x and y that work for xry but don't work for y/x.
Yeah, so if you just simply negate that, you get there exists an x and a y such that x is less than or equal to y and y is not less than or equal to x. So what I'm getting at here, Nathan, is that your explanation about why the relation is not symmetric was sort of an abstract explanation. But to show that a relation is not symmetric, you have to actually come up with an example. So your reasoning that you spoke of is sort of sound reasoning, but at the end of the day, you've actually got to come up with just a concrete example. So can somebody give me an example that would be the proof or the counter example that shows that the relation is not symmetric? That's the kind of thing that's a concrete example. So then 2 is less than or equal to 3 is true, but 3 is less than or equal to 2 is not true. Or sorry. So we could say that 2 is less than or equal to 3, and 3 is not less than or equal to 2. So again, with proofs that a relation does not have some property, the general sort of reasoning is okay, but it doesn't really qualify as, it's sort of harder to do that, and also ultimately it it's not sufficient to, to show that a relation does not have some property. You've actually got to give an example, even when it seems like a no-brainer. Still, you gotta show the example. All right. So what about transitivity?
It is transitive. So if it's transitive, then if XRY is true and YRZ is true, then XRZ must be true. And because of the transitive, you can even just do the transitive property of equality for at least the equals to part. If X is equal to Y and Y is equal to Z, then X is equal to Z. And then less than, like, if X is 0 and Y is 2 and Z is 4, then 0 is less than 2, 2 is less than 4, therefore 0 is less than 4.
Yeah. So everything was fine until the end, where you sort of caved and started talking about actual numbers. The deal is that this is basically comes from the axioms of real numbers. What you said before, the equality part is simple. It's just the transitive property of equality. If X equals Y and Y equals Z, then X equals Z. We just get that from the axioms of the real numbers. And then there's the transitive property of inequality. If X is less than Y and Y is less than Z, then there's a property of real numbers that says that X is less than Z. And then it's just kind of a tedious combination of things. Well, what if X is less than Y and Y equals Z? Then what do you say there? Well, the deal is that that kind of stuff we won't get too fussy about. So basically, for some of these, you can just punt and say, well, yeah, this is just a basic property of real numbers. All right, let me give you another relation. This, just to give you some more practice. So how about this one? This may seem strange. So the relation is defined by this equation. So is there some nicer way of explaining how that relation works? Can any of you think of a way of explaining this relation in sort of words, or making it simpler? The hint is what can you say would have to be true in order for this equation to be true?
Either X or Y has to be 0.
Or one more possibility.
Or Y minus X is 0.
Yeah, and what has to be true for Y minus X to be 0? Can you say that in a different way?
X and Y have to be equal.
Yeah, exactly. So x equals 0 or y equals 0 or x and y are equal. So what would the graph of this relation look like? Keep in mind the graph is going to be a subset of the xy plane, and it's going to be the set of all points that have this property or that have that property or that have that property, and it's the inclusive or, so you allow even for cases where more than one of those is true. So what would the graph of that look like?
Would it just be, the x axis, the y axis, and then the line y is equal to x?
Yeah, exactly. So let's see if I can. Oops. So those are the three lines in the plane that have that have those equations. So that's the graph. So based on the graph, can we see if this relation, what are the properties of this relation? Is it reflexive? Is it symmetric? Why? Is it transitive? Sienna, you've been a little quiet. What do you have to say about this one? Can you weigh in on this? Is this relation reflexive?
Yeah, I think it would be.
Good. Now, explain why in terms of the graph or in terms of the equation.
I mean, well, we already have that y equals x. So then when you just like plug x back in, that's obviously going to be true.
Good. Yeah. And in terms of the graph, what would you say?
I'm not sure on the graph.
Eden or Nathan, you want to weigh in on that?
Would it just be some point along the line x is equal to y, just a point along there, and since it's along that line, therefore it has to be true? Or
Yeah, well, it's actually got to be this. The idea is that that entire diagonal is part of the graph. So every point on that diagonal is part of the graph, and so that means that what Sienna was saying was that for every x equals x is true. And so x is true. That's in terms of the equations. In terms of the graph, the graph contains every point of the form x comma x. That's the whole main diagonal. Now that's important because the other day, well, on one of your, whoops, shoot, hello. There was a graph on one of the videos here's the graph of a relation. So this is the graph. Well, actually, before I say, does anybody remember what graph this is the graph of? I mean, what relation this is the graph of?
Would that be xy is not equal to 0?
Exactly.
X times y? Yeah.
Yeah. So the only time xy equals 0 is when x equals 0 or y equals 0. So notice that this graph, oops, shoot, dang it. This graph contains every point on the main diagonal except it's missing this point on the main diagonal. So for most pairs x comma x, x is related to x, but there is one pair on the diagonal that's missing. So 0, oops. 0 is not related to 0, and it's kind of a tongue twister. It's because 0 times 0 is not equal to 0 is false. 0 times 0 equals 0. And so since it's missing one point on the diagonal, this relation is not reflexive. So this is just kind of a reminder that when you look at the graph, when you're looking for reflexivity, you're making sure that every point on the main diagonal is in the relation. All right, so on to symmetry. Is this relation symmetric? Can you explain in terms of the graph, and can you explain in terms of the definition, the equations? How does the graph have to look for a relation to be symmetric? The graph of a relation in the xy plane.
Does it have to like mirror each other? So like whatever appears on one side has to appear on the other side? Something like that?
Yeah, can you be more precise though? Mirror, I mean, there are lots of on the other side of what?
On the other side of either, x is equal to 0, y is equal to 0, y is equal to x, y is equal to negative x, something like that. Some sort of line that goes through the origin. It has to be symmetric over.
Eden and Sienna, what do you think of that? There's something, part of what Nathan said was right, part of what he said is not right.
I mean, I think, from what I can remember, like the xy, but not xy, the y equals x, like line is usually like indicates symmetry, I think, because if you put, because like since y equals x, if you have like x is related to y, then y should be related to x because they're the same number. So I know like on graphs, I'm pretty sure that like the x equals y plane is the symmetric line.
Yeah, so Nathan, what you're referring to is the general definition of symmetry for shapes. For, you know, we say that a shape has some kind of symmetry if there's some line that you can flip the shape across and the shape doesn't change. But for relations, we're talking about exactly one line. So for instance, if this is the point A comma B, then this is the point B comma A. And so symmetry is A R B, then B R A. So if a point A comma B is on the graph, then the point B comma A, sorry, I've made a mess of my drawing here. Then the point B comma A also has to be on the graph. Now those two red points that I drew are not on our graph, but you get the idea. Symmetry for a relation is just this one particular kind of symmetry that is, does the graph have is it its own mirror image across just this one line? And so graphically, this graph is I've got too many pens available. So we'd say that, Nathan, you know, back to what I was pestering you about, we'd say that our graph is reflexive across that line, or our graph is symmetric across that line. In other words, that line y equals x is a line of symmetry for our graph, and so the relation is symmetric. And Nathan, what you were talking about is, you know, yes, it's true that there is another line of symmetry. The line x equals 0 is a line of symmetry, but that has nothing to do with the fact of the relation being a symmetric relation. We're only talking about this one. Now, can anybody want to grapple with describing this proving that this relation is symmetric just abstractly using the definition of the relation? I wanted to bring this up because it's actually kind of a blast from the past. It brings up stuff that we haven't talked about so much. It came up in the discussions. We learned about this in chapter 4. But it has come up in chapters 6, 7, and 8. So anybody want to weigh in? How would you do an abstract proof? Again, it's always good to be able to do different kinds of proofs. In this case, the nicest proof is to draw the graph and just say, look, the graph is symmetric. But it's also good practice to be able to do different kinds of proofs, because in other situations, other kinds of proofs are better. So can anybody weigh in on an abstract proof that relation is symmetric? Can anybody weigh in on how that proof would have to start and how it would have to end? Good, I'm glad I brought this up. So So there's the statement of symmetric. So what would be the structure? What would have to be the, now here I'm talking about, I wrote this sentence in the context of the previous relation, but this is the generic statement that a relation is symmetric. So what would have to be the structure of a proof that a relation is symmetric? What would be a structure of a proof for that circled statement? How would it have to start and how would it have to end? That's all I want to get at right now. Anybody? Well, remember what I talk about in the videos all the time. We start by introducing a generic particular element. So we do this. Suppose that X is related to Y. So that's the hypothesis. You know, or maybe I should say, suppose X and Y are real numbers such that X is related to Y. So then how is this proof going to have to end?
I guess it would end that y our x would be.
Yeah. Great. Now, the thing is, let's work forwards. That's a defined term. So what's going to have to be in statement 2?
Just the definition of the function or of the relation.
Yeah, so what is that?
It would be, I guess, quantity y minus x times y is equal to 0.
Yeah, and we could also do the word version. So we could just say that x equals 0 or y equals 0 or x equals y. Now, let's work backwards. Here's a defined term. Maybe I'll do that one in black. In order to prove that that is true, what would we have to have previously said?
I guess similar thing, x is equal to 0 or y is equal to 0 or y is equal to x.
Yeah, so I'm going to do it in the exact same order. Y equals 0 or x equals 0 or y equals x. So you see that there's nothing to do here except, I mean, so how do we get from this statement to here? Well, why am I allowed to change the order of these things? That's because the OR operation is commutative, so that's no big deal. So we could, you know, oops, shoot. In other words, there's no gap here. We're ready to go. We're ready to number this as our statement 3. But we just need to give justifications. It's by statement 2 and the commutative property of the OR. That's why we're allowed to move this one over there and that one over there. But what about this? Why are we allowed to do this?
It's just I guess, symmetric property of equality.
Yeah, symmetric property of real number equality. Right. So there, there are all these different properties. The symmetry property of the relation is what we're trying to prove, but it involves this one step, which is the symmetric property of real number equality. So maybe I should so that's the way it is a lot of times with relations involving real number equality, that the symmetry property of our relation R has somewhere in it something that depends on the symmetry property of real number equality. And go back up to this. Why was this true? That's what's called the reflexive property of real number equality. So the reflexive property of our relation has at its heart this one step which comes from the fact that real number equality is reflexive. Okay, so back to this. This proof in the end there's really not much to it. I mean, we had no choice but to start the proof this way and to end the proof this way. And then we had no choice but to include this green statement because that's what that green symbol actually represents. And we had no choice but to include this black statement because that's what that symbol actually represents. And so once you put in all this stuff that is required, the middle step is really all that we had to come up with was the justifications. There actually was no gap. There's just a missing justification. So this idea of thinking about proof structure, for these properties of relations and their proofs, it's a great testing ground for this idea of are you focusing enough on the idea of proof structure. All right, so those are both two abstract proofs and also graphical proofs. The fact that this relation is symmetric, or the fact that it's reflexive, we could argue in terms of the graph, and we could also do an abstract proof. And the fact that the relation is symmetric, we could argue in terms of the graph, and we could also do an abstract proof. Now, is this relation transitive? I'll give you a hint, it's not. Can anybody prove that this relation is not transitive? Now remember, a proof that a relation does not have a property has to be a counterexample, because the proof that the statement that a relation has some property is a universal statement for all blah. Well, actually, let's just write some stuff down.
Yeah. Well, so in order for x or y to be true, I can make y equal to 0 and x equal to some real numbers, let's say 1. And then for y or z to be true, I can make y equal to 0 and z equal to some real number 2, I guess. And then x or z would not be true because neither x nor z are equal to 0 and they're not equal to each other.
Fantastic. So let's great. So let me write down the so transitive means that for all x, y, z, if x are y and y are z, then x are z. And not transitive there exists an x, y, z such that x is related to y and y is related to z and x is not related to z. And so the key thing here is this: there exists. You got to show me an example. So Nathan's example is perfect. And so you can think about how to, and Nathan's explanation of it was also perfect. You got to always have in mind that when you're talking about this stuff, you're often going to be talking about it with somebody who might not be quite clear on the concept. So you got to hit them over the head with it. So you say, let x equals 1, y equals 0, and z equals, sorry, did you say 1? I think you said, yeah, 1. And z equals 2. Now, z doesn't have to be a different number. Z could be the number 1 also, but that's okay. And so then you even want to hit the reader over the head with it even more. So what are they supposed to make of this? Well, that notice x x are, oh, sorry, yeah, x r y is true because y is equal to 0, and y r z is true. It's because y is equal to 0, but x r z is false. As Nathan said, because neither x nor z is 0. Okay. Now we've been talking about relations a bit. How about let's touch a bit on functions. Who's with us? Sienna, Eden, are you still there?
Yeah, I'm still here.
No, Eden had to leave to go to another class.
Okay. Anybody else join us? Is it just the 3 of us?
I joined.
Who's that?
That's Blake.
Oh, great. Hi, Blake.
Hello.
Blake, we've been talking about relations so far.
Okay.
Now, functions, properties of functions. What does it mean for a function to be one-to-one? And onto. I like the words surjective and injective and surjective. Can somebody jump in and give me a definition of either one of those? There's more than one way. I want to talk about these. I want to talk about different ways of saying these things. And also, you can feel free to weigh in on what's the incorrect way of saying, because that's also important. The as important as what is the right definition is to remember that there's sort of a very tempting wrong definition.
For one-to-one, if f of x1 is equal to f of x2, then x1 equals x2.
Fantastic. Great. And what's another way of what's an equivalent? So this is if the two outputs are the same, then the inputs must have been the same. Now, what's an equivalent statement? Well, the contrapositive. It's this. If x1 is not equal to x2, then f of x1 is not equal to f of x2. So that would be if two inputs are not the same, then the resulting outputs are not the same. We're going to come back to that. Let's go onto. Can somebody tell me the definition of onto?
Is that where, every output f of x is or has a corresponding image x that it goes to? Something like that.
You're kind of buzzing around the right ideas. First of all, you said image. You'd want to say pre-image, but the thing is, you started by saying for every output f of x. The thing is, we're really, you got to make sure that you think about the y's. You don't want to say for every f of x, because then you sort of given away the store. What you want to say is for every y. Oops. There is an x such that y equals f of x. So Nathan, when you said for every f of x, well, if when you're doing that, you're already limiting yourself to only looking at the things in the set y that are outputs for some x. The thing is, we want to look at every y, and because there might be some y's that are not f of x, that are just y's that cannot be achieved as an output. So the definition of onto is for every y can actually be achieved by doing y equals f of x. So for instance, if you think about this y equals x squared, that's f of x equals x squared. We can let y equals -5. That's not an f of x. There is no x such that f of x equals -5. So you want to say for every y there is an x. Now, can anybody express this in words using at least or at most? Well, let's go the other direction. What would a quantified statement look like? the quantified statement for onto is this: for every y, little y in set capital Y, there exists a little x in set capital X, such that this is true. Now the key thing I'm getting at here is this means at least one x. So if you want to put this in words, for every little y in set capital Y, there is at least one x in capital X, such that y equals f of x. So the key thing is this at least one. Now go back up to this. Can anybody formulate a sentence having to do with the one-to-one property that is analogous to this sentence that we just formulated for the onto property?
Would it be for every y that is in the set, or that is an element of y, there is at most one x?
Exactly. Fantastic. Yes. For every y that's in set capital Y, there is at most one x in X, such that y equals f of x. So I'm gonna do that in red. So this sentence that we just wrote does not say that there are any x's. It just says there is at most one. So for instance, let's think about the graph of y equals e to the x. Notice that, so let's call this f of x equals e to the x. Now I use this notation in the videos. I don't think it's introduced properly in the book. But are you all comfortable with this notation? So do we still have who all's here? Is it still Nathan? Is it Eden who had to leave?
Yeah.
So Sienna, you still there, and Blake?
Yeah.
Yep.
Okay. Are you all comfortable with this notation? Do you recognize what? Do you understand what it says, or what it's about?
Is that just a statement of the domain? So like, in interval notation, f would go from negative infinity to infinity.
Yeah, this is just a statement that says so this symbol just means this. It's I call this an arrow diagram, and it's just a way of concisely saying that this symbol little f represents a function. Now, notice that, well, who can say whether this function is onto and in terms of a horizontal line test?
If you're talking about, like the area below y is equal to 0, it's never gonna get there. So I guess it wouldn't be onto, at least for those codomain ranges.
Yeah, so to make it official, notice again the statement that a function is onto is a universal statement. The statement that it's not onto is an existential statement. So you've actually got to give, got to show me the number, show me the y that's in the codomain that is not achieved as an output. So let y equal, say, -5. Well, so then in terms of the graph, that would be down here. So you'd say there is no x in the real numbers such that e to the x is -5. So in terms of the graph, this horizontal line does not touch the graph. So in terms of the sentence, for every y in the set of real numbers, there's at least one x such that y equals f of x. Well, that's false. There are no x's such that 5 equals f of x. Now, is this function one-to-one? And can somebody address that in terms of the graph?
So it is 1-to-1 because on the graph, I guess every y value has at most one x value that's associated with. So for y is equal to 0 and less than 0, there is no x. The graph never touched it. There's no x's associated with it. And then for values of y greater than 0, there is exactly one value on the graph that kind of touches it.
Exactly. So for y equals b, where b is greater than 0, this line touches the graph, but only once. So I wanted to bring this up because back to the definition of one-to-one, for every y, there's at most one x. That's not saying that there is any x. Here's a y equals -5, for which there is no x, such that y equals f of x. Here is a y, y equals 3, for instance. For that y value, there's exactly one x. But the thing is, for every y, there's never more than one x. That's the statement of one-to-one. So the reason that those two are neat to think about is for the purpose of articulating the definition of bijective or one-to-one and onto. Add another page here. So think about this, the definition of the definition of one-to-one is for every y in set capital Y, there's at most one x in set capital X such that y equals f of x. The definition of onto is that for every y in set capital Y, there's at least one x. And so if we put those together, a function that's both one-to-one and onto, or that is both injective and surjective, would be a function that for every y in set capital Y, there is exactly one x in set capital X. So the book says a one-to-one correspondence. That is, so the definition is both injective and surjective. That is both one-to-one and onto. And that is this, for every y in set capital Y, there's exactly one x. In set capital X, such that y equals f of x. And so in terms of the quantifiers, for every little y in set capital Y, there exists, you put the exclamation point, there's exactly one x in set capital X, such that y equals f of x. So go back up to the definition of surjective. The definition of onto was this quantified statement. For every y, there exists an x, and that means at least one. And so the definition of one-to-one and onto looks almost the same. It's this whole big thing. The big difference, the key thing is there's this exclamation point, which means there's exactly one. And so, so that's, maybe I should say this. So this material, is really about just sort of the skill of really carefully parsing these symbols. It's sort of finicky, and you can go through life not ever having to deal with one-to-one and onto, but the thing is, it's very careful parsing of these different symbols that makes you realize the difference between these terms. And that's the skill, that reading skill of paying attention to this dense symbolic notation for math, that is the real takeaway from a course like this, that you bit by bit train your eyes to be better at noticing very subtle differences in mathematical expressions. All right. Hey, now what about, okay, it's 12:15. We've been about an hour and 15 minutes. Let's go on a little bit more. Let me see here. So how are you all for the business involving compositions of functions? So F composed with G, G composed with F, and properties of those compositions. Do you want to talk a bit about that stuff?
Honestly, I feel pretty confident with that. That's not the first time that I've seen composition.
Okay.
Yeah, I feel the same way. It's I think I've been over that before, so I'm not the worst, or I'm okay with that.
Okay.
Yeah, I think I'm okay as well on it, so we can probably just gloss over that.
Let me bring up one thing though. There's a diagram that's really useful that came up in some of the homework. This diagram got used a couple of times to prove different things. Can anybody remember what it was used for? Doing a terrible job of my drawing. Anybody want to weigh in? So notice in terms of function diagrams, arrow diagrams, we have f is a function from x to y, and we have g is a function from y to z. Now what about g composed with f? That's a function from x all the way over to z. Now this diagram came up when talking about properties of compositions. What do you notice about this function and its properties? Well, the key thing is that G composed with F is injective. That is, it's one-to-one. because, well, what does that mean? It means that if two inputs give the same output, then they must have been the same input. But there are these two inputs, and there are no cases where two different inputs give the same output. So another way of describing injective or one-to-one is that if two inputs if two inputs are different, then their outputs are different. So so this is definitely an injective function. Also, G composed with F is surjective. That is, it's onto. You look at all the elements of set capital Z. Every one of those has an input that will give that as the output. Now, having started to write this stuff, can anybody remember why this diagram was interesting? What does it illustrate? Well,
Both.
what's interesting? Oh, go ahead, Blake.
I was just gonna say both are injective and surjective.
Wait, say it again.
Like G composed of F is both injective and surjective.
Yeah, but there's something interesting about this. What about the individual maps? G composed with F is injective even though G is not injective. See, this map is not injective. There are two inputs to G that give the output of Q. It's possible for a composition to be injective even though the map on the left is not injective. Now, what about the second statement? G composed with F is surjective even though F is not surjective. So look at this. Every output does have an input in the set capital X. So the composition is a surjective, or it's an onto map. But look at this element of set Y. There is no element in set X that gives an output of 3 in set Y. So so this map is not an onto map. So it's possible for a composition of maps to be surjective, even though the map on the right is not surjective. And again, back to the other one, it's possible for a composition of maps to be injective, even though the map on the left is not injective. But the thing is, there are closely related theorems that say it doesn't, you can't do this with both maps. That is, if a composition is injective, then F must be. So look at this example. In this example, the composition, start over, make it, the composition is injective. If the inputs are not the same, then the outputs are not the same. Well, in this example, the first map, that is the map that's on the right in this composition, that map is an injective map. So so there's actually a theorem that says if the composition is injective, then the map on the right of this symbol has to be injective. And if G composed with F is surjective, then G must be surjective. So that is the thing on the left has to be surjective. The thing on the right does not have to be surjective, but the thing on the left has to be surjective. So if you look at this map again, this map G composed with F is surjective. Every element of Z has an arrow that hits that element. Well, so that means then that all those arrows are coming from set capital Y, and so that means that the function G, which is sending those arrows, has to be a surjective map. So this collection of 4 facts, the fact that this is a theorem, and then there are these things that show, you know, the cases where the other map doesn't have to have that property. That's an important set of things to keep in mind. And so this one diagram is really cool because it gets used very simply to illustrate these 2 key facts. The proofs of these theorems are a little bit more difficult, but the proof that this stuff behaves this way is wonderfully shown with this one very simple diagram. So it's nice to have a simple diagram that can be used to illustrate more than one thing in math. So that's one of my favorite diagrams in this course. I guess we should stop there. We've been almost an hour and a half. Any questions? No, there were no questions earlier or requests. I guess, well, Nathan, you had a request that we discuss relations. Are there any requests at this point, or should we wrap it up? All right, well, I guess I'll wrap it up. I'll post the recording, and tomorrow is the exam. Send me messages today if there are questions that come up. All right, thanks everybody.
Thank you.
All right, thank you.
See, I'll stop recording.